Hello, all my honors chemistry students. Today we're going to be talking about equilibrium expressions. Now, we completed this activity the last couple days where we made graphs of different reactions taking place. And what we found at the end here is that if you look at this amount of B, which was the products, which started at 0 in this particular graph, and then the amount of A, which was the reactants, which is reduced as the reaction goes on in this particular graph. The interesting thing is, no matter how much you start with of A and B, whether you have all A and no all products and no reactants, or you have equal products and equal reactants, what you find is that once it comes to equilibrium, your A and your B on each of the graphs are the exact same numbers. And we see that on this bottom chart. At equilibrium, you ended up with 2.5 moles of your reactant and 7.5 moles of your product. And so if you take the ratio, you see those ratios are all exactly the same. The next thing that's really interesting to see is that this ratio holds true even if you start with a different number of moles. Up here, your total was 10 moles for each of these, but here now in part D, we only had 8 moles, and in part E, we only had 4 moles. As long as your percentages are the same, so as long as you have the exact same chemical reaction going on, then your ratios are also going to be equal. For further proof, we noticed here that this F through J was a totally different reaction with different percentages. And in this reaction, we ended up with 6 different moles of products than reactants, but the ratio of these was always 0.50. So in 1864, some Norwegian chemists came up with what they call the law of chemical equilibrium. And this states that at a given temperature, now it's important that we keep this temperature constant for this, and in a closed system, with a chemical reaction, it can reach a state of equilibrium in which the ratio of the product and the reactant concentrations has a constant value. So in our last example, what we saw is the top chemical reaction had a constant value of 3.0, and the bottom chemical reaction, which was a different reaction, had an equilibrium constant of 0.5. So if you're given an equation where you have A moles of reactant A plus B moles of reactant B in equilibrium, so we have the double arrows meaning that the forward and reverse reaction are going on at the same time, it's going to create C moles of product C plus D moles of product D. Now, you may not have an A and a B and a C and a D on each side, but you get the idea here. Now, the equation they came up with, the equilibrium constant expression equation, KEQ, equilibrium constant expression, equals the concentration of the products divided by the concentration of the reactants. And we have to include the mole ratios of these as well in order to get this to be a constant value. Now you notice, if the reaction favors the products, if you have more products than reactants when it is at equilibrium, then KEQ is greater than 1. That means you have more products than reactants. If you have more reactants when it has come to equilibrium, then KEQ is less than 1, which means at equilibrium you have more reactants. So again, in our activity that we did in the first part where the KEQ was 3.0, that means we had more products when equilibrium was established. With our second group, it was 0.5, which meant that we had more reactants when it reached equilibrium. So to do the complete KEQ expression, we're going to do the concentration of C, which is one of the products, raised to the power of C, times the concentration of D raised to the power of little d, the number of moles of D in the balanced equation, divided by the concentration of A raised to the power of A, times the concentration of B raised to the power of B. Now this is a very important thing because this is concentration. We are only going to include gases and aqueous solutions, because solids and liquids are 100%. They don't have a concentration. So again, we're only going to include gases and aqueous solutions. So today your assignment is to write out the equilibrium expression for the following. We're not going to plug in numbers yet, we're just writing expressions, and it would be best if you do this on your own paper because there's really not room on this sheet. But I'm going to do a couple for you as examples. So let's look at the first one. This is a gas, this is a gas, this is a gas. This is called a homogeneous equilibrium. So the KEQ for this expression is going to be the concentration of water, which is a product, raised to the power of the coefficient, so that's squared, divided by the concentration of the reactant. So the first one is H2, hydrogen gas, squared, times the concentration of O2 gas. And it is just to the first power because there's only 1 mole of O in our balanced equation. Let's skip down to a heterogeneous equilibrium. Let's skip down to number 10. So you see here that the equilibrium constant here includes some solids, so I'm not even going to include those, only the gases. So the KEQ expression is going to be the concentration of CO2 squared divided by the concentration of CO squared. Those are the two gases. Not too difficult. Now let's skip down again to one more where we have, let's go to number 15, where we have some aqueous solutions. So we're going to include this, this, and this in the expression, but we're not going to include the water. So the KEQ for number 15 is going to be the concentration of CH3COO minus times the concentration of H3O plus divided by the concentration of CH3COOH. Now your assignment is to do the rest of these.